Let's proceed to the third illustrative problem. Let me read it to you, for you, I should say. So, a rectangular scow 9 meters wide, 15 meters long, and 3.6 meters high has a draft in seawater. So the specific gravity of seawater is 1.03. The draft in seawater is 2.4 meters. Its center of gravity is 2.7 meters above the bottom of the scow. Determine the following in the initial metacentric height to be the righting or overturning moment when the scow tilts one side is just at the point of submergence. So let's try to analyze the situation first. So we have a scow or a barge. So usually barges are used as a temporary placement of cargoes sa mga ports, seaports. Nilalagay yung mga cargo pansamantala before they load it to the ship or before they transport it inland. Okay, so we have a scow now, and we have two sides in here. We have two sides. So when the scow floats in seawater or water, whatever liquid it floats, we have two sides in here, and we're going to usually we analyze it in terms of these two sides. We have the longer side and the long-sided and the short side here, and we usually analyze the more critical side, which is actually the short side. Let's try to look into this illustration. So if we try to analyze the short side, the barge or the scow would tend to roll. The mode of failure, we call it rolling. So it would roll, ganun. Pag nag-overturn siya, mag-roll siya pag ganun. And the long side, if you consider the long side, ito yung view niya, long side view, I should say. So, it would, the mode of failure would be overturning then, what we call it pitching. If you try to visualize which side is more critical, it's actually short side. It's the short side that is more susceptible to overturning. So we call that rolling. So oftentimes we analyze the floating body in terms of the short side. If it is stable sa short side, most probably it would be stable along the long side. So in this problem, we will try to analyze the short side, okay, the short side of the scow. So again, we are solving for the initial metacentric height. Metacentric height is mg, distance between the metacenter and the center of gravity. So that's letter A. So it's a further discussion. So let's try to consider the short side of the scow. Ito yung illustration natin for the short side. So we solve for the initial metacentric height, okay, distance between the metacenter and the center of gravity. So initially, we assume m to be above g or higher than g. So if that is the case, mg, distance between m and g, which is the metacentric height, is mbo minus gbo. Ayan. So sabi sa problem, g is 2.7 meters above the base ng scow. So may load siguro yan. So basically yung g is no longer the centroid of the shape, no? Pero mas mataas na siya. Because of course, merong load dyan, nakalagay ng mga cargo dyan. So basically, G would shift based on the amount of load that would be put dun sa scow. So G is 2.7 meters above sa bottom ng scow. And of course, BO would still be located at the centroid of the displaced volume. Okay, so draft is given to be 2.4 meters. So BO then is equal to 2.4 divided by 2. That is 1.2 meters from the bottom of the scow. 3.6 meters yung thickness or height ng scow natin. Ayan. So by inspection, mg is mbo minus gbo if m is higher than g. So by inspection ulit, GBO is equal to 2.7 meters minus 1.2. That is 2.7, yeah, location ng G from the bottom, minus 1.2. That's GBO. So we solve it by inspection. And we solve for MBO since meron naman tayong rectangular, meron tayong formula for rectangular section. Let's just use that. Or you may also use yung general formula to solve for MBO. Okay, since wala pa namang siyang tilt. So MBO is equal to B squared over 12D times the quantity 1 plus tangent squared theta over 2. Theta here is 0 since hindi pa naman siya nag-tilt. So MBO is 2.8125 meters. So yeah, okay, so MBO is higher, or M is higher than G based from if we compare GBO and MBO, MBO is greater than GBO. So basically, M is higher than G. So tama yung initial assumption natin. MG is MBO minus GBO. So that would be 2.8125 meters minus 1.5 meters. So our initial metacentric height when the scow is still floating up in the apart position, that is 1.3125 meters. That's the initial metacentric height, mg. Now, letter B, we solve for the righting or overturning moment when the scow tilts one side is just at the point of submergence. So, pag nag-tilt yung scow, yung isang side niya na fully submerged na siya. So, yan. That's the condition. So, what would be the righting or overturning moment? So, righting moment yan if M is higher than G. Overturning moment yan if M is lower than G. So, first we need to solve, we need to know or identify muna if M is higher or lower than G. So, we solve for the righting over or overturning moment by this particular formula. We have discussed this before. So, Rm or OM is equal to W times X, or that is BF times X. Ano yung X ulit? That is equal to mg sine theta. So, ito yung value ng X, distance between the two forces, the coupled forces. So, yan. So, mg sine theta. So, that's how we solve for the righting moment. W, this can be W or the weight or the buoyant force. Anyway, they're just the same naman. Okay, so by inspection, okay, GBO doesn't change. So, ano yung GBO mo kanina? GBO natin kanina, ito. Okay, hindi naman siya nag-iba. Hindi naman nadagdagan or nabawasan ng cargo. So, GBO would still be the same. Okay, so that's 1.5 meters. Now, ang mag-iiba is the value of MBO. Since mayroon ng tilt yan, so, mag-iiba na ngayon yung MBO. So, pwedeng M ay mas mababa na siya sa G or pwede pa rin mas mataas sa G. Ano? Okay, so first we need to solve for the angle of tilt. Kailangan natin yan sa pag-solve ng MBO at the same time sa pag-solve ng righting or overturning moment. So, we need to solve for the angle of tilt. That is equivalent to, so, if you look into the figure, this is the angle of tilt. Theta here is also equal to ito, yung tilt na dyan. So, if you try to transfer angles, analyze the problem. So, yung theta dito, yung displacement niya, yung angular displacement niya dito, theta dyan, is also equal to this angle. Ayan. So, we can solve for that angle knowing that we can solve for this side. That's 3.6 minus 2.4 yung side nito. And this is yung half nito, that's 9 meters yung total width ng scow. So basically half of that is 4.5. So we can solve for the angle theta by tangent function. So we can so tangent theta is equal to opposite of the adjacent side. So opposite side would be 3.6 minus 2.4. The adjacent side is the half of 9, that's 4.5 meters. So angle theta will give us 14.931 degrees. Now we can solve for MBO now. So MBO is equal to B squared all over 12D times the quantity 1 plus tangent squared theta all over 2. So substitute na natin sa equation or sa formula. Now may value na yung theta. So MBO would be different from the first MBO when the barge or the scow is still in the upright position. So MBO is still higher than GBO. So that means that the moment created by the couple is a righting moment. So righting moment siya. Okay? So stable pa rin siya. So the moment created by the couple is a righting moment. Okay. Next is to solve for mg, the metacentric height. Kailangan natin yun para ma-solve ang distance between the two forces, x. Yan. So x here is mg sine of theta. And so mg by inspection is equal to mbo, okay, minus gbo. So mbo minus GBO. So by inspection, mg yan, is equal to MBO, ito, distance ng dalawang yan, 2 points MBO, minus GBO. Okay. So that's how we solve for mg. mg is 1.412 meters. Now we can now solve for the righting moment. Hindi pa pala, we still need to solve for the weight or the buoyant force acting on the scow. No? So, solve natin yung buoyant force. So, it's equivalent to gamma of the liquid times the displaced volume. So, gamma ng liquid, ang liquid is seawater given yung specific gravity ng seawater. Displaced volume is equal to 2.4 times 9 times 15. So, yung displaced volume natin, yan. Yung volume nitong tilted, ito, equal din yan dito. Ayan. Equal din yan dyan. So, we can solve for displaced volume. Kasi itong nabawas dito, yun din yung nadagdag dito. So, basically, yung volume ng upright pa siya is also equal to the volume ng tilted na siya. Yung displaced volume ng upright pa siya, ito, is equal to yung displaced volume ng tilted na siya. So, yung nabawas dito na wedge ay napunta dito. So, yun. Parehas lang yung volume ng upright at nung nag-tilt na siya. Ayan. So, then kinuha yung displaced volume na yan. So, buoyant force then is equal to, ito na, 3273.7932 kilonewtons. Equal yan sa weight which we need to solve for the righting moment. Ayan. So, righting moment is equal to Wmg sine theta. It is equivalent to 1,191.038 kilonewton meter. So, yan na yung righting moment caused by the couple, weight, and the buoyant force. Ayan. Okay? So, the last illustrative example would be discussed in a separate video.